Okay, are there questions on what you have heard in the morning? Okay, so let me at least summarize the results that we had gotten. So, first we used the symmetries to fix the form of the near horizon geometry of an extremal black hole. So, near horizon geometry of extremal black hole. So, the metric was then all the scalar fields were constants. So, we wrote phi alpha equal to u alpha. For the gauge fields, okay, the only non-zero components were fi theta phi, which we took to be pi sin theta. The fact that it is proportional to sin theta is fixed by symmetry. These are constants. And the RT component was given by ei. Sorry, R Fi or RT rho tau. Yes. Right now we are doing classical, so we don't really need gauge fixing, right? We are writing in terms of gauge invariant objects, right? We didn't write what the expression for AI is, right? So if I have to write the expression for AI, then you have to choose a particular gauge, right? Because defined AIs are equivalent, you can add the gradient term, but I'm specifying the field strength, which are gauge invariant, right? So for specifying the field strength, I don't need to pick a gauge, right? So that's the reason I'm using field strength here. Okay, because the gauge fields need not be invariant under symmetry, right? Because gauge fields are not physical, right? Field strengths have to be invariant under symmetry because those are gauge invariants. You cannot change them by gauge transformation. So given this, we define a function. I'll just change the notation a little bit. Now define a function E, which is a function of u alpha, v1, v2, ei, qi and pi. This is defined as 8 pi square. Okay, this factor will become clear later, hopefully. Right now, it's just the overall normalization. Okay, L is the Lagrangian density. Okay, so this quantity will be a function of all these variables because the fields depend on these constants, right? So as a result, L will also depend on these constants. And then we said that u alpha, v1, v2, ei are obtained from, if I write it, this line will be visible at the back or no? Maybe I write it here. Okay, this equation del E del ei equal to 0 basically implements that qi is equal to del ei of v1 v2l, right, which he said is a definition of the electric charge. That's not visible. This one is not visible. Oh, the because it's too small. Okay. Maybe I write it in. Oh, blue is also not very good, I think. QI. This is visible or not? Is it okay? So is this clear? So this is what we had gotten last time. Okay. I just change the name, and then the point is that E is given by the entropy is given by E at the extremum. E means entropy, right? So, but this is entropy as this is not quite the entropy as yet. Right? This is what we call the entropy function. It's a particular function of all these parameters. Once you impose these conditions, then it becomes entropy. Okay. So these we follow from equations of motion, right? This follows from the definition of charge. This one we have not shown yet, right? Right now, let's just take this for as given, right? Because this will also have to explain this 8 pi square factor, right? Right now, let's just take this as given. So let's just check this first. Test this in Einstein-Maxwell theory. So there, the Lagrangian density was 1 over 8 pi g r minus 1/4 So you substitute these forms, okay, and you will compare with what we had gotten earlier. So p is 0. Okay, we substitute the substitute. Okay, we could keep p, but earlier, if you remember, we had said that we had no magnetic charge. Here, setting p equal to 0. So exercise R is given by 2 V2 inverse minus V1 inverse. Okay, you just take this metric. Okay, calculate the Riemann tensor, and then from there, the scalar curvature. Okay. And R will be given by this. And 1/4 f mu nu will be given by Okay, here V1 plays a special role because F has component only along the ADS2, right? Because Pi is 0, right? So F has component only along ADS2 and ADS2 metric has V1, right? So when you contract indices, you have to raise by G with upper mu, right? That gives you 1 over V1 square. So that's this. So V1 and V2 are these parameters, just constant parameters. Right now, so all of these are constants, right? Because I am just trying to determine what those constants are, right? This is a postulate that consists of the general symmetries, right? Just the isometries of ADS2 times S2, right? And we are trying to determine what these constants are. So E will be given by 8 pi square times QE minus V1 V2 . Okay, just from this formula. From this definition of E that I have given here, there is only one sum Q times C, right, minus V1 V2 L, right? L I have already gotten here, right? From this I can calculate L and substitute. This is our entropy. This is our entropy function. And now the idea that you have to extremize this with respect to the parameters E, V1, V2. These are the three parameters. Okay, so these are the three equations that we need to solve. Okay. Simple exercise. Solution is E equal to Q and V1 equal to V2 equal to 8 pi GQ square. Okay, that's an algebraic equation that you can solve. And S, which is E at the extremum, right? So you have to substitute all this. Okay, once you substitute all this, we get 4 pi square Q square. Okay, I'll leave it to you to check. Okay, earlier results been the one we discussed on the first. On the first day, we have taken the Reisner-Nordstrom solution and then taken the extremal limit, right? And we've gotten the expression for the entropy and the fields and so on. You can check that this agrees with that. The difference is that here we didn't solve any differential equation. On the first day also we didn't solve any differential equation, but the solution was given by somebody, right, who had actually solved the differential equation, right. The form of the radial function 1 minus a over r times 1 minus b over r was obtained as a solution to a differential equation. Here you don't need it. Okay, if we are willing to use the symmetries of the near horizon geometry. Yes. That this function will be the entropy? Yeah, this is. Yeah. So, this I am going to discuss later. You can derive it classically. I mean, there is a for generalization of a Beckett-Snarkin formula, which is called the Waltz formula, right, which includes the higher derivative terms. And starting by manipulating the Waltz formula, you can derive it. Right? But it's easier to see from a quantum gravity path integral. So, that's what I'll discuss later, right? How we see this from gravitational path integral. Okay, so this, as I said, has not been derived, right? I didn't derive this expression. Are there questions? So, let me now tell you what form these functions take in the theories for which we calculated the black hole microstates. We counted the black hole microstates, right? The heterotic on 6-dimensional torus and type 2 on 6-dimensional torus, right? Those are the theories in which we constructed the black hole microstates. So, apply So, in both these theories, we counted the microstates and I also gave the formula for the asymptotic expansion and I said that it agrees with the Becken-Snarkin entropy, right. But I didn't tell you how to calculate the Becken-Snarkin entropy, right. So, what I am describing now is how to calculate the other side, right. We got the result from the microscopic counting, okay, but to compare it with black hole entropy, we have to find out black hole entropy, okay, and that's what we are going to describe now, right, by using this procedure. Is this clear? Are there questions? So, you have to first see what the fields are. So, the relevant theory in both cases contains several fields. Okay, I will now list them. Okay. Now, when I say relevant theory, right, in both cases there are additional fields, right, but those are all set to 0 in the black hole solution. So, I am not going to write them. Okay, I am just going to set them to 0 from the beginning. So, the relevant part of the theory itself is reasonably complicated. So, first it has two scalars, A and sigma. Okay, this is called the axion dilaton. Then it has scalars from GMN, DMN, These can be written as 12 by 12 matrix M, okay, which are all functions of x satisfying while L is a fixed matrix 0. This is 6 by 6 identity matrix, 6 by 6 identity matrix and 0. These are real fields, all real fields. Yeah. So these A and sigma are also real fields, and M is also real matrix. So when I say the scalars are represented by a matrix, right? It's in the same spirit that sometimes you can have scalars written as vectors, right? If, for example, you have, say, a three-dimensional a vector of some internal symmetry SO3, right? You write it as a vector. It's not really vector in space time, right? But vector in some internal space. So the scalars, writing this as a scalar is also like that, right? It's a scalar 12 by 12 matrix are scalar, but they are all internal space. As far as space time is concerned, they are really scalars. Right? These don't carry any mu index. Then it has 12 gauge fields, or let us say vector fields, massless vector fields, like the electromagnetism. And of course, it has metric. So this is a field content. Yes. That's in sigma. Yeah. So sigma is basically exponential of the Dirac field. Okay, and the axion comes from this dualizing the two form field in 4 dimensions. So a Lagrangian density for this is reasonably complicated. Let me write it down. So a Lagrangian density is 1 over 2 pi alpha prime. So the dilaton appears as an overall multiplicative factor. Okay, so metric I am denoting by capital G mu nu. So this is what is called string metric, but you don't really need to worry about this. Here you are summing over I and j. Yeah, I think the only thing that has not been defined is F tilde. F tilde is basically the what you call the Hodge dual of F, right? You take the 4 index antisymmetric tensor and contract with F, right? That's what is F tilde is. Pardon? Yeah. So M is a 12 by 12 matrix, right? And L is a 12 by 12, L is also a 12 by 12 matrix, right? So you take that object. So this is a function of the scalar fields, right? So RG is the Ricci scalar, scalar curvature, yeah, Ricci scalar, right? Constructed from this matrix G that I have introduced. So that's why I come for RG. Yes. Yes, because you are looking at it from the 4-dimensional viewpoint, right? The GMN and BMN have gone into this M. Okay, because those are scalars from the 4-dimensional perspective. And similarly, GMU and BMU have gone into these 12 gauge fields, right? Because M runs from 4 to 9, right? 6 internal index for G and 6 internal index for B. Those have been combined into this vector fields, right? And this is something you can derive, but I have not, of course, derived it, right? This is the result that I am quoting that you get by starting from the 10-dimensional axle and rewriting this in the 4-dimensional language. So, if you have to solve the equations of motion in this theory, right, it will be quite complicated because as you can see that the scale, there is a coupling between scalars and gauge fields, right? The gauge field kinetic, that quadratic term in the gauge field depends on the scalar field, right, which is not what normally you have in the Einstein-Maxwell theory. But now we are going to apply the formalism where you make the near horizon ansatz, right? That's consistent. That's according to the symmetries of the near horizon geometry. So, near horizon so we take sigma as some constant US, A as some another constant, let's call it UA, Mij is a constant matrix, UMIJ. We'll take the metric to be so this alpha prime over 16, right? This is just an overall constant. It was not necessary. I could have absorbed into the definition of UR and T2, right? But it's just a convenient to keep this here, just to cancel off this 1 over 2 pi alpha prime that we see in the expression for Lagrangian density. And then for gauge fields, we take the general answers Fi theta phi. Okay, so the idea is that now we take this form of the solutions and compute that function E that I introduced earlier. E will be 8 pi square and now we have to put this alpha prime over 16 V1 V2 L. Okay, because instead of V1 I have V1 times alpha prime over 16, sorry, alpha prime over 16 square. So this is still complicated because you have to evaluate L, okay, for that configuration. Okay. Nevertheless, okay, RG you can in fact calculate using the previous formula itself, right, because the form of the metric is the same, right. So I wrote down the formula for R, right. Remember R was V1 inverse minus there is a 2 V2 inverse minus 2 V1 inverse. We use the same formula except that there is extra alpha prime over 16. So you can calculate R here. These terms vanish because sigma and A are constants. All scalar fields are constants on the horizon. And in the horizon, these terms are just vanish. Okay. Similarly, this term vanishes, right? Because M is constant. M is a scalar field, it's constant on the horizon. Right? You can see from there that I have just taken this to be some UM. This term is non-zero, right? So this will contribute and this will contribute, right? So the contribution will come from here, here and here. So this I leave as an exercise, but it's not very easy, difficult to do. So I'll change these brackets to curly bracket. Okay, so this is the form of the function that you have to extremize. And then so you have to now solve del E del EI equal to 0, del E del VI equal to 0 for I equal to 1, 2, and del E del UM IJ equal to 0. Okay. So this is the only slightly complicated part. It's complicated because EM has a constraint. Remember that you had a constant M L M transpose equal to L, right? So UM being the value of M also satisfies that constraint. So this part you have to do a constant variation. right, to solve this, but nevertheless it can be solved. Okay. And then E gives the entropy. Okay, so using this we can find the entropy for a black hole carrying any charge, right. You take arbitrary 12 dimensional vector Q, arbitrary 12 dimensional vector P, okay, solve this and you can find the entropy of the black hole. Okay, you have to still solve these algebraic equations, but there is no differential equation to be solved. Yes.
Empty is equals to, is this something like a similar transformation for real matrices?
It's not quite the similarity transformation for real matrices. Okay, M also has another condition, M transpose equal to M. This is, so there will be EM transpose equal to EM. It's not similarity transformation. Basically, right, what it reflects is the following. You see, M is a 12 by 12 matrix, right. Imagine that you have imposed a symmetric 2 by 2 symmetric condition, right. So, a 12 by 12 symmetric matrix, you will still have 78 components, 12 times 13 by 2, right, 78 components. Okay. This is representing the scalars GMN and BMN. Okay. GMN and BMN are 6 by 6 symmetric and 6 by 6 antisymmetric matrices, right. So, total number of such matrices, such components, independent components is 36. Because AMN runs over 6 values, right. So, GMN plus BMN is an arbitrary 6 by 6 matrix. So, there are 36 components. So, 78 is too many, right. So, it couldn't be that an arbitrary symmetric 12 by 12 matrix captures G and B, right. And what we can show is that once you impose this extra condition, ML M transpose equal to L, right, then it reduces the number of components from 78 to 36, and those are the ones that now can be related to GMN and BMN. Okay, so this condition basically you have you can write down an explicit expression for M in terms of G and B, right. I just haven't written down because it's complicated, but from that it also follows that MLM transpose should be identically aligned. Is this procedure clear? Right. So, this gives you the entropy for arbitrary Q and P, arbitrary charges. Now, let us relate this to the states for which we counted the microstates for heterotic theory. So, the state for which the counting was done in heterotic theory is the one which where the charge Q is a 12 dimensional vector takes the following form. So, recall that we had said we have to look a particular state, right. It carries some electric charge of B6 mu, B5 mu, some magnetic charge of B6 mu, B5 mu and so on. Okay. So, those charges, once you know how these gauge fields arise from the compactification, those charges can be related to these 12 dimensional vectors Q and P, the charges that you get in this 4 dimensional from a 4 dimensional perspective. And once you follow the translation, right, from 10 dimensional fields to these 4 dimensional fields, the statement is that the particular charge for which you have done the counting has this form, right. 0, 5 means that it's a 5 dimensional column vector, so each entry 0, right. That's the convention. 0, 5 means a 5 dimensional zeros. So, it's a altogether a 12 dimensional vector, 0, 5, then minus n, then 0, 5, then minus 1. P is also a 12 dimensional vector, 0, 4, 4 zeros, then 1, then 0, then 4 zeros, then q minus 1, and then minus j, right? You remember that these n, q, and j were the three numbers that we had that was characterizing the state in the hadronic theory. Okay, other charges were set equal to 1. Okay, so that those ones you see here, right? The sum of the charges that were set equal to 1. So the idea is that you take the general expression for the entropy that you found from here. Okay, that is known for arbitrary 12 dimensional vector P and arbitrary 12 dimensional vector Q. But then you can evaluate this for these particular vectors, and the result is what I had quoted earlier. Okay, this is the result as I wrote down last time, right? This result is what you also obtained from the asymptotic formula, taking the counting formula, right? And then doing an asymptotic expansion using the steepest descent contours. That's the result that I had quoted. Okay. But the same result comes from a completely different analysis. Then we just calculate the black hole entropy using this procedure, and you get the same result. Yes. J is one of the charges that I had introduced last time, right? We had three charges, N, Q1 and J, right? Various components of B6, B4, B5, G4 and G5, right? One of them was J. Yeah, so that J translates to this last component of P in this language. Now, as I said, this formalism is also applicable to type 2 black holes that whose counting I described this morning. So this one, in fact, I can leave as an exercise. Because this is just a classical extremization problem, right? We have these things for fixed Q and P. We extremize with respect to every other variable, right? And then just see what E evaluates to. Horizontal. I think I forgot a normalizing factor. Q is 1 over 8 pi. Okay, in fact, you should have probably caught me earlier, because you see there is a 8 pi square sitting here, right? So if there is no pi in that formula, right, then by extremizing this, there is no, you could have gotten a pi, right? You would have gotten something proportional to pi square, right? Because of this 1 over 8 pi in Q, this becomes a pi, okay, which you see here. So for the type 2 black hole for which you did the counting, okay, and the entropy,
What is the significance of writing 0 and then 0, 4?
Nothing really. I can write to 0, 5. Yeah. Either it is sometimes useful to think of the 6 and 6. Right? That's why I wrote it that way. Yeah. It's 5 doubles and 0. Any other question? Now, this is good that we reproduce Bekenstein-Hawking entropy, but once you have this formalism, we can in fact go beyond Bekenstein-Hawking entropy. Because this formalism that I gave, this formula is valid for any Lagrangian, right? So, and in string theory, typically you get the Einstein gravity coupled to scalars and vectors at the beginning, but then there are higher order corrections, right? For example, corrections that are proportional to the square of the Riemann tensor, which you don't have in the ordinary general relativity, but string theory has those terms. Okay, their effect is small, but they are there. So you can ask what is the effect of those terms on the entropy. Okay, and you can use exactly the same formula to calculate it. So I'll give an example now. So in heterotic on T6, we have alpha prime corrections. We have corrections to L, okay, and the first correction has the following form. Where this is the usual Riemann tensor and this is a function. So I'll explain what I'll write what this function is. So chi of A sigma is in fact a complicated function. It's minus 1 over 64 pi square. Where eta is a well-known function which is called the Dirac eta function. Okay. Eta of tau as a complex variable is okay. See, let me repeat it. Eta is a function of one complex variable, eta of tau, which is given by this. Okay. And the correction to the Lagrangian that you have has this complicated function of this pair of variables A and sigma multiplied by a particular combination of Riemann tensor, Ricci tensor and R, which is called the Gauss-Bonnet density. Okay. And this function chi is given here. Okay, it's given in terms of eta. Yes. You have to do the string one loop calculation, right? So you are trying to calculate the correction to the string effective action, and string one loop correction produces this function. So there is a completely systematic procedure for calculating this and also the higher order terms, right? At higher order, there will be terms which involve even higher parts of the Riemann tensor, right? And again, their coefficients can be calculated. Okay, but for now, let's just consider this term. The question, yes.
Sorry, actually, L is
This part is a Gauss-Bonnet term, and it's multiplied by a function of the scalar fields A and sigma. No, because it's multiplied by this function of scalars, right? So it's not topological, right? So that's why you can actually calculate it, because it actually contributes to the S matrix, right? Because it's a function, non-trivial function of the scalar fields. So is this statement here? Okay, so the statement is that a string action, okay, once you go through the string theory calculation, has, besides the term and the Lagrangian density that I wrote down, corrections, right? And the first correction, which has two extra derivatives, is of this kind. And given this correction, one can ask what is the correction to the entropy? Because E will change now, right? Because Lagrangian density is changing, and L entered the expression for E. So correction to the entropy. Okay, so this is a correction to the entropy in terms of the charges. Okay, because entropy, of course, will have to be a function of the charges only. Right? And the way these charges appeared, here it was a function of A and sigma, right? But if you look at the near horizon, what values A and sigma take on the horizon, these are the values of A and sigma on the horizon. Right? That's why this correction appears in this form. Right? Because A and sigma at the horizon are fixed in terms of the charges.
So, 64 pi square comes from
64 pi square comes from, yeah, there's an 8 pi square in the multiplying the whole thing, right? So that enters this formula, right? And then there are some additional factors of 8 that comes from evaluating this combination, right? This has to be evaluated on the inner horizon, right? That gives an additional factor of 8.
is that now is something.
Yeah, this is a function that also appears in the partition function, right? In fact, this appeared earlier when you wrote down the various counting formula. Right? But in this case, it's not coming from a counting formula. It's just coming from calculating the string effective action, one loop on correction to the string effective action. Okay. But now that we have got this result, this correction, we can ask, does it have anything to do with microscopic counting? Right? We did the microscopic counting, right? And we got the result. We have in fact the exact result, right? Because we have the exact expression for omega. Okay. And we discussed how to extract the behavior for large charge, right, which is use the steepest descent contour. So to calculate corrections to this, you have to take the same steepest descent contour, but start calculating the corrections to the steepest descent results, right, which is the do the integral using around the steepest descent contour. And when you do that, right, you find that this is exactly same correction appears in the counting formula. So the counting formula doesn't change, right? Whatever formula that I had given you yesterday is the full formula. But when you expand this for large charge, that expansion, what I showed you, what I stated yesterday was only the leading term in that expansion for large charge. Once you go to the next order term in that expansion, you get exactly this correction in that formula as well, right. So, this basically is showing that the agreement between entropy and microscopic degeneracy is not only true for the Vacancy-Norton formula, but all the corrections to the Vacancy-Norton formula, okay, due to higher derivative terms. And this in fact has been tested. This is also true in many other theories, in a wide class of theories. This is for heterotic. Okay, for type 2 there is no such correction. Are there questions?
Stuck is J, really, words.
How are they? Oh, J and Q enter the expressions for the Q's and P's, right? But A and S, for A and sigma, right, which are the Near-Hausen scalar fields, they are determined by extremizing the that function, right? E. E depends on P and Q, right, and hence also on J and N. So, through that, when you actually solve for A and sigma, you find that A and sigma are basically takes these values. Right? That is the reason why here you had a function of chi, which is a function of A and sigma, but in the near horizon geometry, A and sigma determine in terms of the charges, and it becomes a function of the charges. Is this clear? Right? So, here there is no scalar fields, right? Scalar fields are all gone. I have written everything in terms of the charges, and that is what the entropy is supposed to be a function of, right? Entropy is supposed to be a function of the charges. So, I described, so this formula is for heterotic string theory and on a 6-dimensional torus, but there are many other similar compactifications which are heterotic string theory on various orbifolds of the 6-dimensional torus, all preserving the same amount of supersymmetry, right, which in this case is n equal to 4 supersymmetry. And for all those cases, this function phi is different in the in gravity, from the gravity side, you get a different kind of connection, but the microscopic counting formula is also different, right. And when you expand the microscopic counting formula, right, you find you get exactly the same function there as you get from the gravity side, right. But the function for chi itself is different, right, both from the microscopic side as well as from the gravity side. Okay, now let me just quickly mention some consequences of this, and then I'll go to the quantum theory. So, recall that S, the entropy is the extremum of E with respect to E is a function. Let me write what E is a function of. Okay, we extremize with respect to these variables. And so this is a function only of Qi and Pi. Okay, the final entropy that you calculate using this procedure is the function only of the charges. But the full black hole solution not just a near horizon geometry. The full black hole solution depends also on the moduli fields. Okay, and the moduli, if you recall, are the vacuum expressions of the scalar fields at infinity. Okay, when you are far away from the black hole, right? That's the meaning of the moduli fields. Okay. So while the black hole solution depends on these moduli fields, okay, what this near horizon analysis tells us is that the entropy is only a function of the charges and doesn't care about the asymptotic values of the scalar fields, right? What the scalar fields were at infinity has no bearing on what the entropy is, right? Because entropy is determined purely in terms of the charges. So independence of these values of S of the moduli is known as attractor mechanism. Namely, the scalar fields somehow get attracted to fixed values that depend only on the charges at the horizon, right, irrespective of what the values were at infinity. And as a result, the entropy doesn't depend on those values. And this is consistent with what I said earlier, that we have this, recall I had told you earlier that we have this line in the moduli space, right. Here the microscopic counting is done. Sorry, here I don't remember which one is where. Here is counting, here is black hole, right, and the result for omega is supposed to be independent as you move around the line. Here you are exploring this region, right, in the black hole region, and here you do see that as you move along the line, the moduli line, the entropy is independent of where you are, right, because this line represents the asymptotic values of the scalar fields. Are there questions on this? The second point I want to emphasize is this spherical symmetry, which I mentioned several times, but I didn't say how supersymmetry implies spherical symmetry. So let me just give the logic. So the black hole has supersymmetry. Has some supersymmetry. And we have near or as a ADS. And as we saw, this implies that we have symmetry SO 1, 2. Now, when you have some set of symmetries, they should form an algebra, right? The infinitesimal symmetry should form an algebra, and the finite symmetry should form a group. Now, once you have some symmetries, you can try to combine them and see if you generate new symmetries, right? Because one symmetry followed by another symmetry is a new symmetry, right? in terms of algebra, if you have some infinitesimal symmetry generator, then commutator of two infinitesimal symmetry generator is also a symmetry generator. Right? And if you take a commutator of two symmetry generators, and if you find that it's not there, you have to add it, right? Because that's also part of the symmetry. So you can ask, given these two symmetries, that you have an SO 1, 2, and we have the near horizon ADS, we have the supersymmetry that we already know the black hole has. If we combine them together, right, what is the minimum algebra that can accommodate these two? Okay, and you already know the existence of these two. So it turns out that the minimum algebra or minimum group it's a group called PSU 112. Okay, we don't really need to know what it is. Okay, it has a name. But the important part of this that we need for us, that the bosonic part of the symmetric group is SO1, 2 times SU2. Okay, and this is the rotation. Okay, so this /2, right, is a reflection of the results SO2. SO2 is the same as SO3, right? As an algebra, there is no difference between SO2 and SO3. Yeah, not as a group, but as an algebra. Algebra, right? SO2 has one extra element compared to SO3, but as an algebra, they are the same. Okay. So what this is saying is that just as a consequence of the supersymmetry and the fact that you have this SO1, 2 isometry, because you have a because extremal black holes have their isometry, implies that you must also have rotational symmetry. And rotational symmetry means you cannot have any angular momentum. So the solution should be rotational invariant and hence no angular momentum. Okay, so these are argument that when you study it from the black hole side, we see that all states are purely bosonic, and hence the contribution of the degeneracy is the same as the contribution of the index, right? Because index is the difference between the number of bosonic states minus number of fermionic states, and because everything carries zero angular momentum, every state is bosonic. Well, this argument I had used earlier, right, to argue why we can compare entropy of the black hole to the index that we would get from the microscopic counting, and so this is basically that logic. Yes.
The process may environment, but that has just invited also.
Okay, so rotational invariant. Now, if we apply the symmetry generator, any SU2 symmetry generator, it means it annihilates the state. Yeah, because SU2, what does SU2 generator do, right? It transforms the solution by rotating it. But because of rotational invariance, it gives you exactly the same solution, same state, right? So if you have a state which is when acted on by an SU2 rotation is unchanged, right? See, if it had an angular momentum and if you apply a rotation generator, it will go to a referred state, right? So the state will not be invariant, right? Rotational invariance here is saying that the state must be invariant under an SU2 generator. Right? You apply the SU2 group action, group element, and it should remain the same state, right? And that will happen only if it is a zero angular momentum state, right? So you can think of it either as a group, that group element should acting on the state should give you back the same state, or as the algebra generator acting on the state should give you 0. The generator is infinitesimal deformation, and under infinitesimal deformation, the state is not changed. Is this clear? Any other question? I have 10 minutes. Okay. Okay, so in the 10 minutes, I will try to give the quantum version of this. Okay. That will justify that formula for the entropy that I wrote down, right? And also will tell us to go beyond and calculate other corrections that you don't see from the classical effective action. So we quantum theory. Okay. And here you are discussing quantum theory on the gravity side. On the microscopic side, you already had a quantum theory, right, which is weakly coupled quantum theory, but now we are trying to see from the gravity side whether quantum effects can give additional corrections to the Becker-Samapti entropy. So quantum theory is based on using Euclidean path integral. So we take tau to minus I tau Euclidean. Okay, and in this case, e to the IA, the Euclidean path integral is weighted by the factor of e to the IA, right? Where A is the action. This becomes e to the A, because this I and integral d tau becomes minus I integral d tau e. So I and minus I combines to give you 1. So this becomes e to the A. So this is the weight in the path integral. So you have the Euclidean solution. So the metric now takes the form V1 . Okay, and in the eta variable, it sometimes easy to write eta variable, it's d eta square plus sin square eta e square plus V2 . Okay. So far, I am just written the classical ADS2 solution, ADS2 times S2 solution in the Euclidean space. Okay, by taking tau to minus tau I tau e. No quantum theory has been done so far. Now, before we proceed, you notice that this one near eta equal to 0 has a structure d eta square plus eta square d tau e square. right? So at eta equal to 0, this d tau is square coefficient is 0. So the solution looks singular, but we are familiar with such singularities in 2 dimension. Can you recognize what the singularity means? Is it really singular? D eta square plus eta square d tau square? Are there metrics for which the coefficient vanishes but it's not singular? Pardon? Schwarzschild, but Schwarzschild is too complicated, right? Think of something simple. It's a 2-dimensional metric. Yeah, 2-dimensional space in the polar coordinate. What is the metric? It's dr square plus r square d theta square. This is the metric in the polar coordinate. Perfectly smooth metric. Okay. But this is smooth provided theta is a periodic variable of period 2 pi. Right? Theta has to be an angle. Right? Otherwise, it's not smooth. Okay. So just by comparing this with this, right? Near eta equal to 0, it's exactly same structure. D eta square plus eta square d tau square. Right? So this is smooth. This is smooth if tau e has period 2 pi. So the ADS to space basically has the following structure. You have the tau e, that is the angular coordinate, and eta is the radial coordinate. Okay, and as long as tau is periodic with period 2 pi, this is smooth. Okay. This is an infinite space because eta goes all the way to infinity. Okay. But what we can do is we can think of this as a space with a cutoff at say a large eta naught. Okay, there is a, let's suppose it's a cutoff. And the way we do quantum gravity in ADS is the following. We say that okay, the original classical solution was this. But in quantum theory, of course, all fields fluctuate, even gravity will fluctuate. But while we integrate over fluctuations of gravity, that's so in the path integral, you have to integrate over fluctuations of gravity of the metric. Okay. But we'll fix the metric near the boundary fixed. Okay. So near this eta equal to eta naught boundary, we'll have exactly this structure. Okay. But then in the interior, okay, we let the metric fluctuate and we integrate over the metric and all other fields. Okay. So metric as well as all other fields, we have the original classical values, right? Whatever you got from the attractor mechanism at the boundary, and then in the interior we let them fluctuate, and that's the path integral we have to do. So the Euclidean path integral is integral over d of all fields e to the power action, okay, subject to the boundary condition that near the boundary it should be whatever you got from the attractor mechanism, right? And so the path integral then will be a function of the charges because the charges fix the boundary condition. The charges q and p fix the values of all the fields and hence they fix the boundary condition. Okay. So this will be some function of the charges. Is this clear? For leading term, is e to the a at the classical solution. And then there are subleading terms which come from analyzing the path integral. When one does this calculation carefully, right, I think I will not have time to do this carefully, right. When one does this carefully, one finds that this leading term takes the form of e to the power minus e to the power 8 pi square sum over I qi ei minus okay, this 8 pi square basically comes from angular integral. You have to do the integral over the action to do the action integral, you have to integrate over this angular direction tau e, which gives a factor of 2 pi, right, and the theta phi integral which gives a factor of 4 pi. That's the origin of this 8 pi square, right. Just simple integral over the coordinates theta, the tau e and theta and phi. So this you recognize as the classical answer that we had found. This is what E was, right. So this is the reason. This is the classical result. Okay. And to this you can also add those hard derivative corrections, right. Those will also be part of this because we have got the hard derivative corrections from this only by correcting L. But now on top of that, you can study quantum fluctuations, the effect of quantum fluctuations, right, and they will also give additional corrections to the entropy. And I'll just mention the result that using these quantum fluctuations, the quantum fluctuations give terms proportional to log of area, okay, where area is the area of the black hole horizon, and in particular this gives you this factor of minus 2 log n. Okay. We'll call it that is the correct formula. Yeah. Okay. It gives no log correction for it, does just cancel heterotic on T6. Okay. And these indeed agree with microscopic counting, because when I wrote down the microscopic formula, if you recall, for the type 2 case I had a minus 2 log n, okay, when you read the expansion, okay, and that comes out of this analysis of quantum fluctuation around the black hole background.
Suppose A is
2A, not boxing, type 2A. Right. This is a particular theory. We discussed two kinds of string theory, right? The type 2A string theory on T6 and heterotic string theory on T6. For type 2A string theory, when we did the asymptotic expansion, we got the log correction, right? Those logs come from this one loop fluctuation, right? Whereas for the heterotic theory, we didn't get a log correction. We got that complicated function chi, right? And that chi comes from there's a tree that comes just from the tree level, but including the hard derivative corrections, right? So just the classical analysis is able to give the heterotic result, but the quantum analysis gives the type 2 result, right? the quantum contribution to heterotic result is 0 to this order. Okay, which is again consistent with what you know from microscopic counting, where microscopic counting doesn't have a log in the heterotic theory. So the result is that so far the microscopic results and black hole results always agree. Okay. And in fact, this also can teach us, because the microscopic results are known exactly, right? As I said, so in principle, you can calculate to any order you like, right? You can just expand in powers of inverse power of charges, and you can get the results to arbitrary order, right? And the question, and in principle, you should be able to produce each of those corrections from path integral in quantum gravity, but you have to go to higher and higher order. So this is a good way to test quantum gravity, right? And also to perhaps learn the rules for doing path integral over quantum gravity, right? Because that itself is a somewhat complicated subject, right? So the idea is that if we since we already know the black hole answer completely, right, by requiring that the quantum gravity results should match with the black hole answer, may be teaching us how to do quantum gravity path integral. Right? To the order that you have done, we didn't really encounter any subtlety. So you can do the quantum gravity path integral just as you do standard quantum field theory path integral. Right? But this may change at higher order. Okay, so I think I'm done.